This is section 3.6, heat transfer from extended surfaces. So the objectives for today's class are to identify the design objective of an extended surface or fin, and to identify the general differential form of a temperature in the fin. So let's start with the concept of an extended surface. So basically we have a solid that is submerged in a fluid. So our solid, it is going to be transferring energy to the fluid. So that energy transfer, it is going to be via convection, but it's coming from the solid via conduction. So there is an actually integration in between the conduction and then the convection. So let me write it down. So we have that Q, the heat transfer due to conduction, it is going to be equal to minus K multiplied by A multiplied by dt dx. So K, it is the conductivity of the solid material. A, it is the area, so we have it here, so this is the area. And dt dx is the gradient of the temperature in the solid. So that heat that is coming from the solid but via conduction, it is going to be equal, if we neglect radiation, it was going to be equal to the heat transfer rate by convection. So by convection, we have the heat rate due to convection equal to H, which is the heat transfer convection coefficient, multiplied by the area and multiplied by Ts minus T infinity, where Ts is the temperature on the surface and T infinity is the temperature of the fluid. So now, for some reason, we need to increase Q. That reason could be that we need to cool down the solid. Like, let's say the solid, it is an electronic device, so we need to cool it down. So we need to increase Q. So Q, which is equal to the Q of conduction and equal to the Q of convection, can be increased by increasing the right hand side, any of the two right hand sides. So we can increase first of all K. If we increase K, it is that we have to change the material. So change material. We can increase H, so the heat transfer coefficient. So to change H in the fluid, we have to increase the velocity of the fluid. So that means put a fan. That's probably the easiest way of doing it. Also, if we decrease T infinity, this difference is going to be bigger, so the Q, it is going to be bigger. So we can also decrease T infinity. So T infinity, decrease T infinity, a colder medium. So that probably in practical means to put an air conditioner. Okay, what else can we do? So we have played with T infinity, we had played with H, we had played with K. So we just need to change the area. So if we increase the area in both equations, it's telling us that the heat transfer rate, it is going to be increased. So if we increase the area, so that will mean an extended surface. So what are the examples of an extended surface? So let's say that we have, this is our original solid. So we are going to transform it in such a way that the total area it is going to be increased. As in this case, the area it was increased by adding some material, and so the total area now it is going to be this plus the horizontal plus the tip plus the sides. So by increasing this surface, we are increasing the heat transfer rate, the total heat transfer rate. We want to increase it. So an extended surface we can say that it is a combined conduction, convection system with the objective of increasing Q, with the objective of increasing the heat transfer rate. Okay, so let's see some examples. So on the left hand side, on the top, we can see this is the motor of a motorbike, and we can see this particularity geometry that is around the piston. So the piston is one of the hottest places, so this is probably the spark, and so we need to lower down the temperature of the piston, and so the surface it is going to have this shape, and it is going to be in contact with the air, the outside air, so that's going to increase the heat transfer rate and therefore lower the temperature in the piston. So that's a typical case. A second case, it is a sink, heat sink in an electronic chip. So an electronic chip is going to be usually very hot. So we put these heat sinks on top of it. So we are increasing the area, and therefore if we have a fan also it will increase the heat transfer rate and cool down the electronic chip. That's another way of having an extended surface. Here is very clear that this was extended as an additional structure to the chip, and in this case is part of the structure. In nature we can find different examples. So one of these is the ears of an elephant. So we are increasing the area, so therefore there is a heat transfer rate in the ear. So also they have a lot of blood vessels that are interchanging the hot blood into the ear, so it is cooling down. Besides, they are also a giant fan. So in the human being, one example, if I try to draw the profile of a person, so this is the profile of a person. So what is the part of a person that is sticking out? Well, the nose. And the nose, it is going to be the extended surface that we know that when it's very cold as today, it is going to get colder than the rest of us. And also our ears. So our ears, there are some extended surface that are going to cool down faster than, for example, our cheeks or our head. Okay. So what is the rationality of the analysis that we are going to do? First of all, let's consider a 1D case. So this is a 1D case. So in a 1D case, so we have a temperature 1 and temperature 2 and probably some T infinity if we have a fluid here. And so there is no heat transfer rate on the sides, so all the heat is coming this way. So if we draw contour lines. So if we draw contour lines of the temperature will probably be like this, because it's 1D, so the different temperatures are just parallel to each other. So if we plot the temperature, so we have, this is T1, and over here we have T2, and in between we are going to have a straight line. Okay, so this is going to be, let me draw a much better straight line. Okay, so this is going to be like a straight line in between T1 and T2. We have done that before. Now, when we have an extended surface, so we have U infinity and we have T infinity. So we have a fluid with some velocity and some temperature. And so now these sides are not insulated. Okay, so there is going to be heat transfer along all this way. Not just on the tip, like in the 1D case. So if this is T infinity over here, so the distribution of the temperature, so let's say we have T1 and this is going to be T2, so this is T2 at that point. It is going to be different from a straight line, so it shouldn't be a straight line. So what do you think it's going to be? Is it going to be something like that, or is it going to be something like that? So we have different options. So stop the video at this point and think, what option do you think it will be? A, B, or C? What's the most accurate interpretation of the temperature in the fin? So is the temperature going to drop faster, or is it going to drop less fast? Okay, the answer, it is going to be A. So the temperature, it is going to drop faster at the beginning, and then it is not going to drop that fast, because the difference in the temperature from the base to T infinity is higher here with respect to the temperature in the tip with respect to the air. So there is not bigger difference of temperature in this side. So the heat transfer rate is going to be less at the tip than it is right at the base. So it is going to drop faster and then less. Okay, let's continue. So this is a simulation of a fin that I made to explain what is actually happening in a 3D situation, or a 2D situation in this case. So we have our base and we have this extended surface, and the extended surface, it is in a fluid which has temperature T infinity. So if we see the temperature distribution, so if we look, so how the heat is moving. So the heat is moving, let me concentrate in one point here. It is moving perpendicular to this isothermal. So this is going to be moved perpendicular, and then perpendicular, and then perpendicular, perpendicular, perpendicular. So the heat is going to move in this direction. So if we take a point right in the middle, so the perpendicular, it is going to be this direction. But if we take a point close to the surface, we can see that the lines, the isotemperatures, have some inclination. So that's why there is going to be heat transfer, there is going to be heat transfer rate in these directions. If it was fully insulated, so this line will be like verticals. So this is the 1D case. So it is not exactly 1D, but we can do some approximation of this system by a 1D equation. Okay, first, before going into some of the equations, let's see some of these examples of different things, different geometries. So we have, this is on gray, it is the base that in which we want to increase the heat transfer rate. So one simple way it is to put a rectangular fin, and the second one it is to have triangular base. The second one, this is especially particularly for tubes, it is going to be like a disc, and this is like a rounded pyramid. So which shape are we going to take? It will depend of different conditions. Like first of all, it will depend of the space that we have. So selection depends on space available, the geometry of the object, for example, it will be much different if we have a pipe that if we have a plane surface. Also the function, what we want it for, also the cost, durability, weight, the weight could be important. So for example, if we have a vehicle like a motorbike, we don't want to do something like very big that is going to increase the weight of the motor. Also safety. If it's sticking out and someone can actually hit it and it's hot, that will be dangerous, so we don't want that. Efficiency. So the shape could be very efficient, but doesn't mean that it's easy to manufacture. So sometimes the manufacturability, it is very important. Manufacturability. Okay, so design decisions are based on all these different items. Okay, let's start with the general analysis. So let's consider this, stop here.